You've probably heard of the Star Trek phrase, "Beam me up, Scotty," uttered by Captain Kirk, normally Captain Kirk, as he requested teleportation back to the Starship Enterprise from some alien world. Now, setting aside my suspicion that the makers of the original Star Trek created teleportation to save money on special effects for spaceships taking off and landing, maybe Gene Roddenberry was onto something. Because the physicist, Chris Monroe, has shown it's possible to transfer information from one atom to another despite those two atoms being disconnected. Chris, who's a professor of physics at the Bice Zetchi Zorn Physics School in Maryland, United States of America, is using what quantum physicists call entanglement. I spoke to Chris Monroe the other day, began by asking him just what entanglement is.
What is entanglement? Well, entanglement is something that is unique to quantum mechanics, and it involves something like a correlation, but it's stronger than that. And maybe I can give a good example. Now, we're going to imagine we have a pair of coins, heads or tails. Each of them can be heads or tails. Now, we're going to make the coins entangled in the sense that your coin always matches my coin, no matter what. Even though your coin seems to be a normal coin, you can get heads or tails. You flip the coin, you get heads or tails. It seems perfectly random, and you have both the aspects of heads and tails, yet it's connected to my coin some way, such that when we both flip the coins, they always end up the same value. Now, that gives you a little bit of an idea of entanglement.
But how do you know when two atoms are entangled? I mean, what is it about an atom which exhibits this property so you can say, aha, yes, that atom is entangled with that atom or that part of an atom?
Well, you can never do it. You can never do it in a single measurement or a single trial. The thing about quantum mechanics is that states can be in superpositions. States can be in this fuzzy state of existence of having two values at the same time.
Is that what a superposition is?
Yeah, that's right. So these coins would be, if the atom is sort of like a coin, the two states of the atom could correspond to heads and tails, and we can have heads and tails at the same time. In fact, both of them are there. Both of them are valid. So you're asking, how do we know that they're both heads and tails at the same time? Well, all we can do is look at it. All we can do is look at the system. And quantum mechanics says that when we look at a system that's in this fuzzy state, it collapses into one or the other. So we can never know by looking at it only once. And this is a lot like a coin. If I give you a coin and I say, is this coin fair or biased? You can never tell by flipping it once. You have to flip it a few hundred times and compare the numbers of heads versus tails. And you can say, well, yeah, it's 50-50. We do a similar thing with the atoms. We look at them, we prepare them identically, and then look at them a number of times and sort of get a distribution of what their states are. Now, the same is true for the entanglement. If I claim that two atoms are entangled, that means if I prepare these two atoms the same way again and again, it's just as I described. We look at both atoms, and they're always the same state. And that's how you prove it's entangled, basically.
Simply by flipping coins.
The atoms are the coin. The atoms are these weird coins that can be
flipping our metaphorical coin many, many times, and we've got a pattern. We say, right, they're entangled.
That's right.
But what is it that creates this? How do you explain this mysterious... Actually, before I ask that question, what bit of the atom are you looking at to see that it's entangled?
Oh, that's a good question. Now, atoms are actually very complicated objects. There's lots of little particles inside the atoms. But we freeze all that out. We're really only looking at a very simplified set of states of an atom. The atom is actually more akin to a bar magnet, the north and the south pole. And in fact, the atom does have magnetism. So it has kind of a magnetic orientation. And in fact, we're basically looking at the orientation of that magnet. Is it north up or north down? And those two states we call a quantum bit because it's not just a 0 or a 1. It can be a 0 and a 1 at the same time. So we're looking at energy levels in the atom that have to do with its magnetism. And you say, what is the entanglement? Well, it's the fact that two atoms, when we look at them, their north poles always line up together, either both up or both down, and so there's sort of a linkage, a hidden linkage between the atoms. Now, it's important that you set up the entanglement. You're not just going to get entanglement for free. You have to have these systems interact in some way, maybe in the past. But the important thing about entanglement is that you can separate the systems in principle, and the entanglement persists even though there's no longer any contact. And this sort of hidden wiring is really what's behind everything in this field of quantum computing, this new field that uses entanglement.
In other words, you say the atoms have to interact. Does that mean that they have to have come into contact with one another? And then once you've separated them physically, then if you get the same result from flipping that metaphorical coin so many times, you can say, right, we've got a pattern here.
That's right. They will have had to have interacted either directly or even indirectly through another particle. Like they can both have come in contact with a third atom, for instance, the same third atom, or the same beam of light. The important point is once the interaction is turned off entirely, you can separate the atoms. You can have one here in Washington. You can have one in Auckland, and they will still be entangled, and that connection will still be there, even though there's nothing physically linking them anymore.
Really? Is there any distance limits on entanglement, or is it infinite? Could this atom, theoretically, these two atoms go to opposite ends, although the galaxy, the universe, doesn't have ends, but could go as far away as possible and still, in theory, be entangled?
Well, as far as we know, there's nothing wrong with that.
Do we know what's happening? Can we explain this, or is at the moment it impossible to explain? You've observed this, but you can't explain why it happens.
Well, that's a difficult question because we can't really. I would say the simple answer is no. We accept very simple rules of quantum mechanics, and this kind of comes along for the ride. And the very simple rules are that everything can be in a superposition. I can be in two places at the same time, according to quantum mechanics, if you can describe me quantum mechanically. And we typically don't describe big things like me quantum mechanically. But quantum mechanics says the reality of any object, the position of any object can in principle be in a superposition of places, as long as you don't look at it. And that's the trick. When you separate systems by a large distance, typically it's hard to do that while not looking, if you know what I mean. So
yeah.
It's not just a conscious being looking and measuring. It's anything.
In other words, once you look at this particular part of an atom, if you look at an atom, then it goes to one position or the other, right?
Yes, that's right. That's right.
The act of our observing the atom affects reality.
That's another way to put it. It's very strange in that respect, and I would say nobody's really comfortable with it, but we accept it, we use it, and there's been no experiment ever disproving that statement, that the observer plays an essential role in the theory.
No, I want to ask you, obviously, very soon about how you put this into practice in terms of teleportation, which is the buzzword that's been used to describe your experiment. I don't know if it's as simple as that, but a lot of people like Star Trek. But anyway, before that though, I want to ask you another question about the atom. Now, when I was at high school, we were shown these models of atoms, and they had, let's see if I can remember, there'd be the electrons spinning around the nucleus, and the nucleus was made of protons and neutrons. Is that right?
That's correct.
Yeah. Now, is that just a model that we've created to try and explain? Do atoms actually look anything like that? Do we have any idea what an atom really looks like?
I would say no. The electron is more of a smeared-out wave. And the reason it has to be a smeared-out wave is that it has to repeat upon itself as it orbits the core. Otherwise, the electron is just going to... the electron is negatively charged. It's attracted to the nucleus. Why doesn't it just find itself at the nucleus? It wants to be there. Well, the reason it can't is that it's a wave, and a wave, like a wave on a rope going in a circle, it has to repeat itself. There are only certain orbits that are allowed, and for the electron to go all the way into the nucleus, it has to occupy an orbit that's just not allowed. There's no way you can make a wave that looks like that. When you hit a drum head, there's a certain pattern of waves. There are other waves that aren't allowed. They're not solutions to the problem at hand, and that's true in atoms. So we tend to think of these little particles that are circling like the Earth circles the sun, and it's really useful to think in those terms, but
that's not what it's actually like. What about the nucleus itself?
The nucleus itself is the same thing. The protons and neutrons are all bound together. They orbit each other just as well when you think of that in that kind of a picture.
And are they particles like say we imagine, if that model of the atom is the planet spinning around the sun and the planets are the electrons, and now you've told me those planets are actually waves. Then what about the nucleus itself? Is it a solid bit of matter?
Well, it has mass, but it's, again, this fuzzy thing of neutrons and protons occupying a wave. And that wave has much higher energies, and, in fact, we don't typically probe those energies in our experiments. Those are, to do nuclear physics, you need much higher energies, X-rays and so forth. So those waves are much more wavy. They're much more tightly confined.
And we can't see these things. We're never going to be able to see what's happening at the atomic level.
If you look at it, it'll pop into one particular state. If you look at an electron, it'll look like it's infinitely small. It's just this little tiny particle. But if you don't look at it, it's this wave.
It's remarkable. It's a wonderful field of science to be in, isn't it?
Just don't think about it.
Right, let's move on to the buzzword, the teleportation. Now, what you've done in your experiment is if I'm understanding rightly, you've transported information from one atom to another, or one subatomic particle to another, using this idea of entanglement. Am I on the right track here?
That's right.
And how does it work? How does your experiment work?
Well, first I should say that teleportation, for better or for worse, is actually a technical term, and it was coined by Charlie Bennett about 20 years ago.
He wasn't a fan of Star Trek, was he?
I presume he was.
Good on him.
It involves, the trick with teleportation is that teleportation does not involve the transport of mass. You're not actually moving an atom from point A to point B. You're only moving its information. And so this brings up the question, well, if you have identical atoms at each end, and you move the information from one to the other, that's just the same as having moved the atom itself. So there's no way to distinguish that. So you might as well have moved the atom from A to B. It's only the information that matters. The state of the atom is the only thing that makes it unique. So it's the state, this state of the particular coin or bar magnet, whatever analogy you'd like. We've moved that state from one system to another, and in the course of doing that, since the atoms were entangled in the middle of that operation, the information never really made the trip, in a sense. It was never you didn't need a wire to transmit that information. And in fact, you couldn't use a wire because you can't look at the information. You have to do it irrespective of what the initial state is. So you have to be very careful the way you handle it. You can't look at it. It can't be betrayed, that information.
I had a look at some illustrations of your experiment, and even those gave me a bit of a headache. Wonderful! It looks like the sort of the ultimate engineer's kind of backyard shed kind of fantasy. I'm looking at it right now. The ion B detection beam, the ion A cooling optical pumping beam. What were you doing when you did this? When you carried out this experiment?
Well, we were zapping these. First of all, these atoms are in a pristine environment. They're single atoms. They're levitated with electric fields. So kind of like a magnetically levitated train. Only it's a single atom and it's not moving. But it's not hitting a surface at all. It's really well isolated. It's in a vacuum chamber, so there's no air. It's sitting there unobserved, and that's the whole point. We set up this complicated apparatus so the atoms can be unobserved, and when we prepare them in these funny superposed states, they persist for long times. They're very good quantum systems when left alone. And so what we need to do is somehow get these two entangled. And we do that by having each of the atoms each of the atoms emit a photon or a particle of light. And we do that by blasting each of them simultaneously with a very fast laser pulse. And the fast laser pulse promotes the atomic electron to a higher orbit, and that higher orbit then relaxes back to where it started. In the course of doing that, it emits a single particle of light, a photon. So each of the atoms emits a photon, and those photons are what we use to make the entanglement, because the photons end up going through optical fibers, and they interact with some beam splitters and detectors and so forth. And after all said and done, the photons are gone. We've detected them; they're out of the system. And because they carried a signature correlation with each atom, their parent atoms, the atoms end up entangled. So we zap each atom with lasers. They emit photons. We detect the photons, and the atoms are entangled.
But you're waiting for the right signal from the photons to show they're entangled. In other words, this is your way of observing the atoms without looking at them. It's
a way of ensuring the atoms are in an entangled state without looking at them.
Yeah.
We don't observe them. It's a trigger. It tells us they're entangled.
The phrase, though, observe, now, is that quite the same as me looking at a piece of paper and seeing it? Seeing the words on the page? Or was this once again a phrase which has a different meaning for somebody who's involved in quantum physics?
No, it doesn't really have a different meaning. I mean, in both cases, you're getting information, and that allows you to measure what's going on in the system. With quantum mechanics, of course, it has this effect of disturbing the system, and that's not true of a big piece of paper.
However, when you're getting the photons coming back, you're able to tell whether the atom is entangled or not. Then what do you do?
Well, when we do determine that the atoms are entangled, they're entangled in a particular way that now that initial information that was in the first atom is now shared amongst both the atoms. So if you remember that before we entangle the atoms, we upload information into one of the atoms. We actually zap it with microwaves that prepare that magnet in some particular state of up and down at the same time. We can prepare any state we want. It should work for an arbitrary state. We don't need to know what it is. But, of course, in the laboratory, we know what it is because we're going to check it out later to make sure it worked. So we prepare the initial state, and then after the entanglement, the initial state is reflected in the correlations of the two atoms. So if we want to say it's 70% up and 30% down initially, now we have 70% up plus 30% down. That's an entangled state. But the 70-30 is now the information that's carried in both of the atoms. And in that way, the information is not in any single atom anymore. It's sort of shared in both of them. And that hidden wiring I referred to earlier is in place now. And the hidden wiring now has the information in it. But it's not really, it's kind of ephemeral. It's not really anywhere in space. It's just in the correlations of these two atoms, even though they could be separated by vast distances.
You're listening tonight on Radio New Zealand National. I'm talking to Professor Christopher Monroe from the Byran Crump. He's a Byran Crump Professor of Physics. Have I said it right, Chris?
That's right.
Now, whereabouts are you based? You're in Maryland in the United States of America, aren't you?
Yeah, that's right. We're near Washington, D.C.
And your experiment, it's about entanglement. It's about using this mysterious quality that atoms have of entanglement to teleport information. Now, you've shown me how you can do it in theory, but does this have any practical implications, or is it just a scientific curiosity?
Well, I would say there are long-term implications of using this to do things that are impossible using conventional means. Now, one thing, I don't see how this could ever be used to teleport big things like humans. And the reason is big things like humans have way too many atoms. And the information contained in all those atoms is just so large that we just can't deal with that amount of information. In fact, we never even think of big things behaving quantum mechanically. So that said, we're limited to small things where quantum mechanics does work with small systems, and this teleportation is it's simply a way to communicate quantum information. And so you might ask, well, why use quantum information, these fuzzy states of 0 and 1? Well, I can list a couple of applications. One is actually out there already, and it has to do with cryptography. If you want to send a message and you want to make sure that it's secret, quantum bits, these fuzzy zeros and ones, are actually very good, because if somebody is listening in, they're measuring. And if they're measuring, they're disturbing the state. And as a sender and receiver, we can tell that. So we can make sure that our signal, if it gets sent successfully, that it was not read. And that's a real-world application. It's cryptography due to the fundamental laws of physics, not due to the fact that somebody doesn't have a very large computer that can break codes. This is fundamentally true. There's no way to break that. So that's an application that's out there right now. Now, slightly longer term is another application called a quantum computer, which doesn't work with just single bits and sending single bits from place to place, but it works. A quantum computer works by dealing with many, many quantum bits, maybe thousands or millions of quantum bits. And since each of the bits can be in both 0 and 1 at the same time, if you put a lot of them together, you can store massive amounts of data in one device. So you can have one memory chip that holds massive amounts of data, and you can do computations on those in parallel. Now, a parallel computer is not a new idea. To do parallel computation, you just buy 100 PCs instead of one, and then you can increase the rate of computation that way. It's kind of brute force. But with a quantum computer, you sort of get that parallelism for free. You still only have one computer. You're just computing on zillions and zillions of inputs at the same time. And so that application, we're going to have to wait some time for it. We have to be able to deal with lots and lots of quantum bits before we can do that. But that's something that is attracting a great amount of attention across the world right now.
Because I guess I'm curious, how do you control the information you put onto an atom if you're going to use it in that way? I mean, what you did was you simply zapped the atom in a certain way, if I'm understanding right. You
right.
Certain radiation, and that creates a certain signal, and that is in its own right a kind of information, but it's not information that necessarily can be used in any kind of code, is it?
Well, it can be, but you have to be careful what you do with it. If you put quantum information in atoms like I discussed, you can't simply then just look at it, because if you look at it, you're only going to get one answer. Yes. And it'll be noisy. It's like flipping a coin. You don't know heads or tails. What you do is you flip many coins, you get them all entangled, and it turns out there are certain applications, and this is why it's a speculative field. There are only a few applications that work this way. They allow all the different fuzziness of the inputs to interfere. Quantum mechanics is a wave theory. We've been talking about how quantum things are waves. Well, waves interfere. You can get crests and valleys, and they meet and so forth. You can get numbers to interfere. The states of this computer can interfere such that in the end, you can get a very simple result. Only one answer is in the end. And when you look at that answer, it can reflect all the complications that are going on beforehand. And so, I mean, that sounds abstract and vague, and unfortunately there are only a few applications that can be put in that form. One of them is very important. It's number factoring, kind of the reverse of multiplication. 15. I give you 15. You can say, well, that's 5 times 3. Yep. But if I give you a super huge number with, say, 1,000 digits on it, you just can't factor that. That's very hard to do that on a computer. You end up having to search pretty much all numbers that are smaller than that to see if they divide. And in fact, that inability to factor large numbers is the reason most encryption standards are secure. They're based on the inability of factoring numbers. So once again, we're back to cryptography. But a quantum computer is able to factor large numbers fast, in theory, if you could build one. And so this is a very big application that's a bit ways off, I would say, a few decades off. We need to develop the hardware to do that.
When you were working on your own hardware and your own experiment, how many times are you flipping these metaphorical coins? How many times are you sending a laser pulse through and getting photons coming back, which are your way of seeing whether atoms are entangled?
Yeah, this is maybe rather embarrassing. I mean, we try to flip these coins about every microsecond, every millionth of a second. And we have to do it fast that way. Well, we can do it fast, but the problem is it almost always fails. We most of the time we don't get the photons to come through the fibers in the way we want. In fact, we have to wait 100 million times before that works. So you can do the math. If it's a millionth of a second, 100 million of those is 100 seconds. So it takes a few minutes for us to teleport a single quantum bit of information, which is rather disappointing, I suppose.
Is that telling us that most atoms are not entangled?
Well, most of the time, it just takes a long time for us to generate the entanglement. You can think of it that way. It's a very slow link. That's the way I think of it. And we have ways, we know how to make it quite a bit faster, but right now it makes it very difficult to think of teleporting bigger objects. You'll have to wait longer and longer using our current technology.
Because I guess I'm curious about the whole idea with how much of what I see, of what I am even, is possibly entangled with something else, somewhere else in the cosmos.
Well, that's the problem, because you're an observer. And so some people tend to think of this quantum measurement problem as forcing us to define what reality is and define what consciousness is. After all, if you want to take quantum mechanics to its limits, you could say, well, fine, there are fuzzy states of existence, and as soon as I look at it, no, it didn't collapse into one or the other. Yes, I did see heads, but maybe there's another universe where I saw tails. So some people think that the universe splits every time you make a measurement, and that neatly solves the problem, I guess, but at a pretty big expense, I would say. We have to now think of other universes, and so there are many interpretations of what goes on, and that kind of makes my head spin. I just tend to think of an observer destroys the system, and there's no way to get around that, and that works. But there's books written about what this means. Einstein wrote a paper in 1935 saying that the title of his paper was it had to do with reality in quantum mechanics. Does it define reality in a consistent way? And his answer, his conclusion was no. Einstein hated quantum mechanics for this very reason. He never accepted it. Unfortunately for him, I mean, there's not a single shred of experimental evidence that it's wrong.
You keep on coming up with things that baffle ordinary minds.
There seems to be a dividing line somewhere. Small things are quantum, yeah, fine. Big things, though, they're indefinite states. We don't. Yeah.
Oh, that brings me to another question, actually, which is what's the limit? I asked you before, obviously, the question. A lot of people who've heard about your experiment are saying, "Well, does this mean one day we will be able to beam up Captain Kirk? Will Scotty be able to do that?" Or is Scotty right when he said that you cannot change the laws of physics? Is there some limit where what's quantum becomes non-quantum? Do we know where it is?
That's a great question, and I just don't know how to answer that. We're comfortable setting a limit somewhere between 1 and, say, 10 to the 25th. And if there is a boundary where quantum mechanics starts to fall apart, that to me is actually more interesting than anything else, any of this quantum computer stuff, because that means there's a new law of physics that we don't know of right now.
There must be some place in reality, it is my little brain is trying to explain to where the physical world that makes sense to me breaks down and quantum physics takes over.
Well, the limits so far really are vast. I mean, there's this big gray area where you just can't apply either quantum mechanics or classical mechanics. There's just no systems. We're just not able to control quantum systems with 10 to the 10 particles. And 10 to the 8 particles is still too small. We can't see it. That's not everyday life. Everyday life is more like 10 to the 20 particles. So it is appealing to consider there being a line, a dividing line. But what sets that line? And that seems really arbitrary, and that's not very satisfying. Physicists like to wrap things up very neatly.
Is it something to do with observation? Is it perhaps the line is where it can be seen?
Where it can be seen, but does that mean by the eye? We see visible light, a very restricted band, and who's to say that there can't be other things that see things much smaller?
I just thought I'd throw that in there. I'm trying to help here. Now, did I read rightly that the military, the U.S. military, have funded some of this research?
Yeah. The military and intelligence agencies, they're very interested in this. A lot of it is for the cryptography angle, and it only makes sense.
Yeah. And
it's not just in the U.S. Throughout the world, I think it's a active area of research. There's an industrial concern in Switzerland that sends single photons to do quantum cryptography. And in fact, I think they relayed the results of a recent election in Switzerland using quantum cryptography to great fanfare. People think there are applications that are around the corner with this technology. Some people think that this field's all hype. It's certainly true that there's interesting physics here. These are interesting systems, and the fundamentals that we talked about of where does quantum mechanics end if it does at all, that's going to be a question that I don't think we'll answer anytime soon. And research in this area, I think, one reason I like this field is that it's going where we haven't gone before. Yes,
to use another Star Trek analogy.
Oh boy, man, there you go.
Where did that come from?
Teleporting a live person. I just don't see that happening. Certainly not.
But what if we look the other way? Maybe it would if we didn't watch. Sorry, Chris. What got you into this wonderful field of science yourself?
Well, many years ago, I got interested in the idea of using lasers to cool, to make atoms very cold. It's called laser cooling. And as a young graduate student, I got involved in a laboratory that was one of the leaders in that area. In fact, my advisor got the Nobel Prize in 2001 for the culmination of that effort. We were able to produce atoms that were so cold, they were millions or even colder, millionths of a degree above absolute zero. So the coldest matter in the universe. And it's a tool using lasers to control atoms like that. And when you do that, the quantum mechanics becomes much more pronounced. And so this field of quantum information science, quantum computing was something different, but the tools of laser cooling and controlling atoms have turned out to be a real boon for this field. And
sorry, Chris, what happens at absolute zero? Do atoms cease to vibrate?
Well, that's how we define absolute zero: the absence of all energy, the absence of all motion. But it's also more of a limit. You can never get there.
Yes.
You can get arbitrarily close, though, but you can never get there.
Because I would have thought that if, as you've been explaining, and if I'm understanding right, atoms, although we use that model from high school of the nucleus and the electrons, that really what we're dealing with are perhaps more waves than solid little bubbles of matter. Yeah. Then if things cease to vibrate, then wouldn't they cease to exist?
Well, they would. I think if things cease to vibrate, it turns out that when things get slower, they get bigger. One thing we learn in quantum mechanics is called the Heisenberg uncertainty principle. If you know that something is going very slow, then you don't know where it is. If you know where something is really well, then you know it's jiggling around. It's another way of describing some of this quantum weirdness. So if everything stops vibrating, then it gets big, and it starts to overlap with everything else, and you get one very funny state of affairs. And since the universe is a finite size, I mean, maybe that does point to a certain limit of temperature. That I don't know how cold that would be. But absolute zero is more of a concept, I think, than anything that's possible.
But there's a lot of concepts that you have to deal with in quantum physics, aren't there?
Yeah, and look, as students in physics, we accept them and move on.
One other thing.
They work well. They work really well. Accept them and
But then, of course, the great thing is you do experiments and they tend to back up the theory. They back up the maths.
No, that's right. Quantum mechanics has survived every test to even high precision. People have measured properties to 12 digits of accuracy that you need quantum mechanics to calculate those 12 digits of accuracy, and they agree with theory. It's rather remarkable.
One other thing I'm dying to ask you is that going back to that sense of matter and the model of the atom, the distance within an atom, how much space is there? If you could, now I know that we've got to think of electrons perhaps as waves rather than particles, but the distance between electrons and the nucleus, is it similar to the distance between, say, a point in a center of a room and the walls of the room, or the sun and the farthermost planets?
Yeah, I believe it's more like planetary stuff. There's a lot of space in there. Electrons are almost, they're point-like. They're really, really small, but their orbits are millions of times larger, billions of times larger. I don't even know which which prefix there, but pretty much everything in an atom is space. That's true, and the mass is very localized to certain places, very much like a solar system.
Yeah. And that amazes me then, that if most of what we see and what we are is nothing, I can do this on the roster in front of me. It's brilliant, isn't it? How do you do? Does this affect the work you do? How do you look at reality, or do you have a pretty down to earth sense of, well, in the end, there is this difference between quantum physics and the physical world that I live in, and it doesn't make you think, oh, am I really seeing what I'm seeing? You're not doubting everything you see and do all the time?
Yeah, maybe I get jaded. As an experimentalist, I do work with two sets of laws. That's exactly right. There's the laws for big stuff, everyday life, like the laws when I'm at home, the laws I follow, and the laws at work, dealing with individual items. They're just different laws, and it's hard to accept that. We don't like to have two sets of laws, but they work and we use them. I don't want to say it doesn't bother me. It's just that I guess I don't think about it all that much, that there's a problem.
If it does bother you, then it bothers you how?
Well, it bothers me in that it seems like there should be something that would unify these two theories, and we just don't know what it is. Now, I say that, but at the same time, I think many physicists, maybe even the majority of physicists, would say that that's nonsense. It's just I don't know what I'm talking about. It's very controversial. People get very emotional about this issue.
About whether there is one, we haven't found that unifying factor and we will one day, and those who say, forget it, it doesn't exist.
Those that say there is no problem with quantum mechanics. What's wrong with you? It's just that the system gets so complicated you can't deal with it. And to them, that's the answer. People are emotional about it. It's remarkable. I don't want to say get into fistfights, but lots of shouting matches.
Well,
why
that'll
waste
be
time thinking about it?
Literally much ado about nothing.
Right. And very famous physicists like Feynman have thought that. You're not asking the right question.
Do you, if you were asked, well, I'm going to ask you, do you think that there is a unifying law that we haven't found yet?
Somehow I don't think so. I just think our understanding is there's something in the framework of our theory that we're not thinking about it in the right way. I don't know. I really don't know. I'm not a theorist.
Does that lead in terms of, does that have any impact on your thoughts about spirituality? Or once again, you're quite comfortable, well, you can sit outside in the physical world and what's happening in the experimental world in the lab doesn't necessarily make you doubt the spiritual side of things in the physical world?
Yeah, to me, those are different issues. I think quantum mechanics is testable, and so when I do this work, I don't tend to question matters that are very deep, like we've been talking about, this divide in the theory, and faith is something else, and in a sense, I don't like to think of them as being I mean, that's just not a scientific question to me. It is compelling, I think, to want to link those two. Some people do that. That it's just beyond science. Science is not equipped to answer such questions, and that's very similar to what happens in faith. And I don't know what to add to that, really. To me, I kind of separate them.
What next with the project, with the experiment?
Pardon me?
What next with the project itself?
Well, what's next? Well, it might sound kind of boring, but we need to collect this light more efficiently. We're getting 1 out of 100 million attempts to work. We want to make that more like 1 out of 1,000, 1 out of 10,000, which still sounds pretty bad. But if we can do that, then we can make many more leaps. We can make many more nodes of these atoms, not just 2, not just A and B, but we could have maybe 4 or 8 that we can move information around in a very funny way and test some very simple quantum computations or quantum communication protocols. So, but there's engineering involved here. We think we know how to do this. We just need to make the experiment better.
In other words, you think the number of entangled atoms you're coming across is more a result of the information you're putting in, the way you're doing the experiment, than the amount of entanglement which exists in the quantum world.
Mm-hmm. That's right. We want to expand the number of particles we're dealing with. And another direction we're looking at is this experiment we did was only over 1 meter. The 2 atoms were separated by about 1 meter. We think we know how to do this over many kilometers. And that has other interesting aspects, both applied in terms of communicating over long distances in a secure way, but also there's some very fundamental ideas. If you can make entanglement over super huge distances, there are some other aspects of quantum physics that you can test involving this distance parameter. So this system looks good in both directions, so we're going to pursue both of those.
And using another Star Trek analogy, do you just need some more power?
That's right. We need to change the color of the light we're using. We're using ultraviolet right now. If we can change that to infrared, it can go further through optical fibers. Very simple as that.
Chris, it's been really interesting talking to you. Thanks very much for joining us.
Okay, it's been my pleasure.
Chris Monroe, professor of the Bice Zecchi Zorn School of Physics in Maryland in the United States of America, on using the quantum mechanical principle of entanglement for the possible teleportation of information between separate atoms. It's kind of like reality only exists when we look at it. Well, was Scotty right? You can't change the laws of physics. But do we really know what those laws are yet?